This is the Earth, the planet on which we, together with more than 7 billion people, are living, and on which we will be living for many thousands of years to come. We do not know much about the interior of our planet, especially about its deeper parts. Look at the deepest well which has been drilled. Indeed, very little compared with the radius of the Earth. We also get information from rocks which are carried to the surface of the Earth by ascending magmas. All remaining information is indirect, provided for instance by seismic waves traveling through the Earth and by gravity or magnetism. We need a lot of theoretical and experimental work to integrate all this knowledge and understand and predict how the Earth works. Seismic waves are a great source of information, and we will make use of them in this course. We will use two types of waves. In P waves, also called pressure or primary waves, the direction of oscillation of rocks is parallel to that of the wave propagation. P waves are thus very efficient and fast. In S waves, particles oscillate perpendicular to the direction of wave transmission and are therefore slower and very sensitive to the degree of coupling between adjacent crystals. Rocks which are partly molten will have very low S wave velocities. We use physical properties to infer the first-order features of the Earth. Temperatures and densities increase with depth, but show a sharp increase around 3,000 kilometers depth. P waves increase from the surface to a depth of around 3,000 kilometers, decrease and then pick up again. She waves have a similar behavior but nearly disappear underneath 3,000 kilometers. Rocks between 3,000 and 5,000 kilometers must be in a partially liquid phase. The depth of 3,000 kilometers is a fundamental discontinuity in the Earth and forms the boundary between the core and the mantle. The two domains have different composition, physical properties, and behavior. The Earth core results from the primary segregation of the gases forming the Earth 4.5 billion years ago. It is formed by minerals very rich in heavy elements such as iron and nickel. It still releases heat, which forms a substantial part of the heat reaching the surface. Relative rotation between the inner and outer core generate the dipolar magnetic field of the Earth and the associated reversals. With the exception of its uppermost part, the domain above the core mantle boundary is called mantle. Nearly 3,000 kilometer rocks of fairly constant composition, substantially different from that of the core. Rocks forming the mantle are very homogeneous, composed of elements such as silicium and aluminium, and of minerals such as olivine and pyroxenes. The corresponding rocks are called peridotites. This results in densities, seismic velocities, and temperatures which gradually increase, moving downward from the surface of the Earth. What is the physical state of mantle rocks? In the plot you see two curves, the geothermal gradient and the temperatures at which mantle rocks melt. With the exception of a small interval around 100 and 200 kilometers, predicted temperatures are always lower than melting temperatures, indicating that most mantle rocks are in a solid state. Despite the fact that they are solid, mantle rocks can deform in a ductile manner, which means without breaking. Indeed, all solids, if given enough time, can deform and change their shape. See, for instance, how glaciers move for kilometers without breaking. Rocks of the Earth will also deform, and over millions of years can even flow without fracturing. Going back to the plot of seismic wave velocities, we see that at depths of 100 to 100 kilometers, values are lower than the underlying and overlying rocks. This is the low velocity zone, a major feature controlling Earth movements. The reason for the low velocity zone becomes clear plotting the melting temperature of mantle rocks and the geothermal gradient. In correspondence with the low velocity zones, temperatures are slightly higher than melting temperatures. which results in partial melting of the rock. It will not surprise you that when seismic waves want to propagate through these rocks, grains will partly move loose from each other, thereby causing a decrease in seismic velocity. The low velocity zone is called asthenosphere. The layer of rocks overlying the asthenosphere is called lithosphere. The asthenosphere is of great importance in geology as it forms a soft substratum on which the strong lithosphere floats and moves. Welcome. Today we will look at the lithosphere. As you remember, we have defined the lithosphere as the layer overlying the low velocity zone. From a mechanics standpoint, the lithosphere is the rigid unit overlying the softer and more easily deformable asthenosphere. Understanding the nature and behavior of the lithosphere is necessary to understand plate tectonics, as well as the formation of mountains and sedimentary basins. How thick is the lithosphere? Is its depth constant over the entire Earth? In the previous class, we have seen that the boundary between the asthenosphere and the lithosphere correspond to the isotherm separating fully solid rocks above from partially molten rocks below. This temperature is usually assumed to be 1300 degrees. The depth of this isotherm and thereby the thickness of the lithosphere depends on the geothermal gradient. In the case shown in the slide, the lithosphere is around 90 kilometers thick. In domains where the geothermal gradient is very high, the 13-degree, 100 degrees isotherm will be shallower and the lithosphere thinner. In regions where geothermal gradients are low, the lithosphere will be thick. Focusing now on the structure inside the lithosphere, you can see a major change in seismic velocities at around 30 kilometers depth. This major discontinuity is called moho and defines the base of the crust. Velocity changes across the moho are of 30 to 50% and occur over very short distances. We know quite a lot about the moho. In some regions, like northwest Italy and Oman, old moho surfaces and adjacent rocks are exposed at the surface where they can be examined. Rocks below the moho have seismic velocities of 8 kilometers per second and densities of more than 3,000 kilograms per cubic meter. These rocks are therefore part of the mantle. Corresponding rocks are mainly peridotites composed predominantly of the heavy and strong Milleran olivine. Rocks above the moho have lower seismic velocities and are much lighter. They are typically gabbros, which are intrusive rocks with no olivine and a lot of feldspars, or metamorphic rocks. But we're not finished yet. While the rocks of the lithospheric mantle are fairly homogeneous over the entire Earth, this is not the case for crustal rocks. Two very different domains are defined, the oceanic crust and the continental crust. The oceanic crust is simple, is typically less than 10 kilometers thick, is made up of three fairly continuous layers composed from bottom to top of gabbros, basalts and sediments, and has young ages, never older than 180 million years ago. The continental crust is much more variable and complex. Thicknesses range from 70 to 15 kilometers. It is composed of a large variety of rocks, mainly metamorphic, organized in a fairly unstructured way, and can have very old rocks, up to 4 billion years. Let us now summarize what we've learned until now, starting from the asthenosphere, which is the layer of partially molten rocks. The entire package of rocks overlying the asthenosphere is called lithosphere, and is characterized by its behavior more rigid than that of the asthenosphere. We mentioned that the boundary between the asthenosphere and the lithosphere is an isotherm, and that its depth depends on the thermal gradient. The lithosphere itself is subdivided in two parts by the moho discontinuity. The domain below the moho is the lithospheric mantle and is composed of cold and strong rocks. Layers above the moho belong to the crust. two very different types of crust are known, the oceanic crust and the continental crust.